Hi everyone, and welcome to the 17th TIA Centre seminar of the academic year. So my name is Adam Shepherd, and I'm a postdoc here at the TIA Centre. So those that are new to our seminars, we aim to invite researchers from across the globe to present new and exciting work. Today, I'm delighted to introduce Ali Mirabadi. Ali is currently pursuing a PhD in bioinformatics at the University of British Columbia in Canada, under the supervision of Dr. Ali Bashashti at AIM Lab. Previously, he earned a double major undergraduate degree in electrical engineering and applied mathematics with honours at the University of Technology in Iran. His research interests lie in areas of deep learning, computational pathology, and mathematical modelling, particularly focusing on representation learning and similarity learning on large-scale pathology data. And the title of Ali's talk today is Graph Structured Pyramidal Whole Slide Image Representation. So Ali, thank you very much for joining us today, and when you're ready, please feel free to start.
Sure, thank you for the kind introduction, and it's a pleasure for me to present our recent work GRASP here in TI Center. So I think I should start. So yes, I'm Ali, and I'm going to talk about this work GRASP, Graph Structure Pyramidal Whole Slide Image Representation. And let's first talk about the pathologist routine while they're diagnosing cancers with whole slide images. So usually when a whole slide section goes to clinic and pathologists want to investigate these cases under microscope, they have to switch different magnifications and consult with different magnification, often going to higher magnification and higher and vice versa, and coming back and zoom out to look for different regions to confirm a solid diagnosis. So there have been a lot of works in this direction, mostly single magnification and some works on multi-magnification. But generally the idea is that people and doctors use lower magnification and higher magnification to diagnose, and and vice versa. So they use this cycle, lower mag to higher mag, and vice versa to confirm the diagnosis. And our question here is that, can an AI model look into whole slide images like a pathologist for basically choosing both magnification to make a diagnosis? So a little bit of background for multiple instance learning here. There are two major methods in the background. One is single magnification and the other is multi-magnification methods. For single magnification methods, we can generally divide them in two groups, graph-based and bag of instance, basically. For graph-based, I can mention PathGCN and DGCN, that these methods are encoding patches and building graphs on patches. And for bag of instance, I can mention a lot of models, and for a few of them, I can mention ABMIL, TransMIL, KLAM, and many more models. And there is like always new models coming out. And these are basically attention-based or transformer-based models that try to model the patches and instances in whole slide images with this type of heuristics. So the idea of this method is basically focusing only on one magnification, usually 20x, which is a bit limited, and this is not the way that pathologists diagnose diagnose in the clinical workflow. On the other side, we have multi-magnification models that we can divide them into groups, hierarchical versus graph-based. In the hierarchical family, we have dual stream MIL, zoom MIL, cross scale MIL, and HIPT. And I think there is like other methods as well. And in the graph-based, as far as I know, there is HIGT and H2MIL. These models basically have a basic assumption is that we follow the information from lower magnification to higher magnification. So zooming in, basically implementing the concept of zooming in, 5x to 10x and 10x to 20x. Also these models, not all of them use 3 magnification. Some of them use a a pair of this magnification, let's say 5x and 10x, sometimes 5x and 20x. So this is a choice for different architecture, and people change it for different cancers and different purposes and based on their design. So the question here is that, can we implement the backward pass as well from 20x to 10x and 10x to 5x? So this is basically similar to zooming out. From 5x to 20x is zooming in, from 20x to 5x is zooming out, if we see it under a microscope. So all of these brings up a few challenges. The first one is that a model should be dynamic in a way that it can freely interact with different magnification. And the other factor is that it should be interpretable. So at least it needs some theoretical grounding on the model's operation, and it shouldn't be biased, meaning that the model should choose the magnification, not us that bias the model toward one magnification in our design. And lastly, the model should have a humanoid behavior, meaning that it should understand different magnification, or in a simpler word, it should understand the concept of magnification the same way that the human interpreted. So I'm going to explain these 4 challenges here. So the first one is being dynamic. So model can freely interact with different magnification. The reason is that we want to have a collective decision-making strategy. For example, in these two patches that we have here, one is the high resolution patch in the right one. By looking at the left patch, we only see that there is a pattern here, but we cannot confirm that which type of anomaly it is. So we need the lower magnification patch to understand that there is a pattern that is forming here, and we can confirm the type by looking at the higher magnification. So we need a collective decision here, because we need to look at both of them to confirm something. Depending to the cancer and subtype, it can change the pattern that they form in the lower magnification, can affect the final decision in the higher magnification. The other challenge is interpretation. So the model, all the designs that we have, they need to have theoretical grounding for the model's operation. It's so common that people in the field use attention heat maps to show that their model is explainable, or at least convince people that model is doing something. But the reality is that attentions are not explanation. And in this paper, attention is not explanation, which is a paper on NLP, they basically show that there is no correlation between the attention weights and the model gradients. So we cannot confirm anything. And usually people interpret attentions as relative importance, but there is no evidence or proof for it to consider it as a explanation for what the model does. But depending to our architecture, it can vary. The third challenge is being unbiased, which means that the model should interact with an unbiased share of magnification. And the reason is that scanning and different protocol in different hospitals can change the sample. And I'm not talking about the staining, I'm talking about other protocols. For example, paraffin embeddings can change the morphology of the scan slide, or even the time that people put the sample in paraffin embeddings can basically change how does it look under microscope. So this is a factor that change 2 samples in the same center, meaning that one sample can have patterns in a higher magnification that you cannot see it in another sample. Maybe you need to change a bit the resolution to see the same pattern even within one subtype. And lastly, humanoid behavior, which what we want is basically that the model can understand the concept of magnification. The first and the fourth one are connected, but the main point of having a humanoid behavior is basically to see if the model is able to understand patterns from patient to patient or subtype to subtype within our data set or not, because we know that Subtypes have some characteristic that is distributed in the data, and in histopathology data, it can be distributed over magnifications as well. So we need to see that if our model is able to understand these differences or not. So with all of these challenges, we came up with GRASP, which has a really simple idea and intuition. And the intuition is basically when we have a whole slide image, we extract in 2 different magnification. We extract patches in 2 different magnification, 5x, 10x, and 20x. 5x representing the lower magnification to 10x that represent the high power. So let's say for the sake of simplicity, we extract 4 random patches. And these are totally random. And then we want to extract the 10x magnification. We extract the patches at the heart of 5x and do the same thing for 20x to extract the patches at the center of 10x to represent the 20x. So we end up with a set of 3 patches that correspond to each other like a pyramid, which the 5x has a larger field of view and 20x has a lower field of view, but a higher resolution. With all of these region of interest or patches, we want to build a graph. So the way that we build the graph is mainly to represent 2 concepts. One is inter-magnification convergence and inter-magnification information, and the other is intra-magnification information. So we basically we connect all the patches from one magnification together in a fully connected graph to represent intra-magnification information in that magnification. And we do the same thing for 10x and connect all the patches in 10x together to represent the 10x magnification, and connect all the patches in 20x together in a fully connected graph to represent the 20x magnification. And each node in different magnification connects to the corresponding node in the neighboring magnification. So this is the 5x node, this is the 10x node, and this is the 20x node. So that's a 3-level graph that each node represents a patch and each edge represents the connection of the different patches. So that's the whole idea of the graph that we built, and the overall workflow of architecture is having a pyramidal whole slide images with 2 magnification, 5x, 10x, and 20x. It can be different sets of magnification, but our primary choice was 5, 10, 20. So we extract the patches from the slide, the way that I described before, and then we extract the features. This feature extractor can be anything. So in this work, we chose KimiaNet and Swim, but it can, of course, change. And then we build the graph the way that I described, a 3-level graph. So I think we have a question here.
Question here, sorry. So in terms of doing this at the whole slide image level, so are these patches all? Is it just 4 ROIs you select, or is it you patch up the whole image to get these?
Yeah, it's random. It basically can be all the patches in the slide.
Okay, and so my question is then, so in terms of the lower level resolution patches, is there a lot of redundancy then in terms of per node, that there's potentially a lot of the same information across many different nodes?
Yes, it can be. The idea is that we cannot limit the lower magnification, but we can put a limitation on the higher magnification. For example, for 20x, we can put this condition that no patches in 20x overlap, but overlapping in 10x and 5x is inevitable. So yeah, patches in 5x and 10x will have overlaps.
Sure.
But still, it depends on the number of patches that we extract there. It can be, if we don't extract too many patches, there is a chance that we don't get any overlap.
Sure, thank you. And we also had there was a couple of questions or comments within the chat as well. So Tilla asked, what is the basis of magnification? Is it objective lenses? I think that's exactly what it is. Is it, Ali?
Sorry, can you repeat?
So Tilak asked in the chat, sorry, that what is the basis of magnification? Is this objective lenses? So yes, I believe that is the case. That's
Yeah,
what
it's yes, it is.
Brilliant. And there's a comment there also from Jack Brian who's asked, who said that there's potentially some uncertainty in the area around one of the papers that he mentioned. But shall we continue for now though? Thanks, Ali.
Sorry, what?
Oh no, please continue. Sorry, Ali.
Okay. Sorry. So yeah, so far we built a data set of graphs that represent the slides, and we want to train the model on top of these graphs. So the idea is that we have these graphs, and we want to pass them through GCN layers. So, and we can use different graph convolutional network, but we pick the simplest one, that is GCN, and is the oldest version of graph convolutional layers. So the idea is that in the first GCN layer, when the message passing occurs, each reference node can see each first neighbors. For example, if we take this as a reference node, it can reach out to the first neighbor and sees all the first neighbors. And then when it passes to the second layer, it reaches out to all the nodes in the second neighborhood. And lastly, at the third layer, it reaches out to the all nodes in the graph. This is because the depth of the graph is 3. So through 3 GCN layers, we can broadcast to all nodes in the graph. But with this design and this architecture, it can theoretically prove that all the nodes in one magnification converge to one node without any need to any pooling mechanism. All the nodes in one magnification converge to one node. So basically, all the blue nodes goes to this node, all the red nodes goes to the red nodes, and same for the green one. And at the end, we do the simple average readouts and pass it to a fully connected layer to predict the subtype. So the theory behind it is this one, that we suppose that all the weights in the convolutional layers are L2 bounded, which is fair because, first of all, our model is converging. So we assume that our model is learning something. So weights are not non-values. And also because we usually use L2 regularizer, our weights are bounded. And the second assumption is that our features, when we build the graph, also are L2 bounded, which means that our feature encoder is basically a really good feature encoder, and it doesn't give us non-values for the feature values. So with these two simple assumptions, we will prove that at the third layer of GCN, these nodes converge to each other. So meaning that the limit of any node in this any layer, for example, in 5x layer, their L2 norm goes to 0, which means that they converge together. And the reason that they converge is that when we do a bit of math, we get to this inequality that is less than these values, which is the weights of the GCN layers, first, second, and the third layer, and the difference between the features in the adjacent magnification. Because our assumption is that our weights are bounded and our features before building the graph are bounded, these are constant values or bounded values. So it is only a function of number of patches. So if the number of patches goes to infinity, or let's say maybe 1,000 patches, because it's to the power of 3, it moves this upper bound towards 0, meaning that this L2 norm will converge to 0. And with that, we will end up with this corollary that basically says that any node in the third layer of GCN converges to one single node, and the same thing for the second magnification and the third magnification. So we will end up with 3 different nodes to represent all the graphs without the need for a pooling layer. So that's the theory behind the intermagnification convergence that happens in the graph. So after broadcasting, we end up with these nodes that converge to a really simple, basically tree here. So to test this idea and this model with this property, we chose 3 different data sets. One is the ovarian carcinoma with 5 histotypes and almost 950 slides, which is a really imbalanced data set with the HGSC being with around 72% of the data. The second data set is a bladder cancer with 260 slides, and it's a fairly balanced data set, but one of the subtypes is really rare, but we try to have a balanced data set. The micropathology subtype in this cancer is rare. The other data set is a public data set, TCGA ESCL, which is a small data set, 135 slides, and it's imbalanced. So for the task of histotype classification, we used KimiaNet, but for benchmarking in this task, we didn't use TCGA ESCA. The reason is that KimiaNet, it was trained in a supervised way on TCGA data. So to prevent any data leakage in our processing, we dropped the TCGA data for this set of experiment. But and also this experiment wasn't only for cross-fold validation. It was a 3-fold cross-validation plus 10 repetition with different random seeds. So we wanted to make sure that the results we get are statistically reliable. And the model is stable in terms of training with different seeds. So at the end, with the model being smaller compared to other models, just slightly bigger than attention MIL, it outperformed on ovarian and bladder on an average. And the same thing with the swing transformer. We used the swing transformer with ImageNet weights. We didn't use those feature extractors that have been trained on TCGA. The reason is that we wanted to evaluate the model's performance to get the information. And if a model has been trained on TCGA, it's going to give you really good features. So it's harder to investigate the models, the graph or MIL part of the model, and see if the model is doing something good or no, it's in the features. So we try to give features that are not really good in this experiment. So the same phenomena happened, except that for ESCA, Zoom MIL was performing better. But on average, the model was again better than other models. With, also, it was smaller than other models. And an ablation study on the magnification to see if the model is capturing multi-magnification information or not. So in this experiment, we basically built graph on single magnification and also a pair of magnification, and we tested the model and saw that yes, the model is capturing more information when it is given with three magnifications for modeling the whole slide image. So there is a few other experiments that are slightly different from typical works that we see in the field. So the first experiment is robustness or stability of the model. So in this experiment, we build random graphs, basically statistically independent graphs. And the first graph was basically we took 10 different patches from the slide for each magnification, meaning that the graph has 30 nodes randomly. And then we build a graph with 60 nodes randomly again. So in each set of experiment, we pick a factor of 3 times 10 of the patches and build the graph, but the patches were randomly extracted from the slide and they were independent in each step. So we repeated this Monte Carlo experiment so that we can show that if the model is stable or not. And the takeaway was that when we increase the number of nodes in graph, over time, the performance increases and also the variance over folds and seed decreases. So what it means is basically, yes, as we increase the number of the nodes, the model gets more stable. But there is a thing here. This plot has an elbow. Basically, after 450 nodes in total or 150 patches per magnification, you won't get any performance improvement. The only thing that that improves is the uncertainty of the model. So model basically reduces the variance and it's more confident in making decision when we increase the number of patches after 450, which was really interesting in these terms. And the other experiment was to make sure that theory of GCN layers is a good choice. There is a phenomenon in graph neural networks that called oversmoothing. So this oversmoothing is basically when we increase the number of GCN layers in a graph, drops the performance. And this is the case for this model as well. So when we have 3 GCN layers, each node can see all the nodes in the model, which is here. We can see it here. But as soon as we increase it to the 4, the performance drops, but again goes up. And the reason is that this graph is building a full graph when it goes to 5. So each node at this part, when we have 3 layers, from this node comes to this node, but as soon as we increase it, comes back here to 4. When we increase it to 5, it can reaches out to this node as well. So basically, it represents, it's like a cycle that we increase it from 2 to 5, and then the shift is 3. And to show that from this part, I wanted to go over that humanoid behavior in models. So we wanted to formulate this based on the gradients. So we wanted to build the histograms that shows the population statistics of the model decision making. So we say let call S as the prediction logit of the model, which is the logits of the output of the model at the end, with S sub C being the logits of the correctly classified graph. For any magnification, we can define the energy of the gradients here. So energy of gradients for magnification 1 is the summation of all the gradients of the nodes squared. So this is a known concept, and basically this is the same thing that people are doing in grad cam to get the gradients back. So the sum of all the gradient squared is the energy of each magnification. And we can, with that, define contribution of each magnification. So the contribution of each magnification is the energy of magnification over the total energy. So this is basically showing that how much gradient the model spent on one single magnification. For M1, the contribution is energy of M1 over the total energy. So the fraction that M1 has been chosen for decision making. And with this concept, we build a histogram, meaning that if a model is totally random, if we initialize the model randomly with uniform distribution and we don't train it, the gradients would be random. So what we expect is basically this energy to be around 1/3 because it's random. There is no pattern there. So the energy will be uniformly divided between different magnification and we will have a factor of one third for each magnification. So the threshold is 1/3. So we say, and we define a error distance and say, okay, if the energy contribution is less than 1/3 minus an error rate, we don't use that magnification. This means that the model is not using that magnification. But if it's more than 1/3 plus an error rate, it means that the model is using that magnification. So there is options that the model is using one magnification or a pair of magnification or no. 3 of the magnifications are important for the model. So with this definition, we plotted this histogram for each subtype separately. So this is the distribution of energy contribution over each subtype. So the blue bars are showing for the subtype micropapillary, and the orange bars are showing for the urothelial subtype in the bladder dataset. What this plot is basically showing is that when it shows 5x, 10x, and 20x, the model is willing to use a multi-magnification setting to make it prediction. But when it's a single magnification, it means that the model has spent majority of its energy, more than 2/3 of its energy, on one single magnification to make the decision. And this is only for the correctly predicted cases, not the misclassified cases. So, and this also matches with the knowledge that we have that for micropapillary, if you show even a thumbnail to a pathologist, if it's a really expert pathologist, they can diagnose micropapillary from thumbnail. It's known to be diagnosed from lower magnification. But the story for urothelial is different because we need to investigate higher power to make the final decision, because it depends to the structure of cell and the texture to diagnose the subtype. So, and the model is roughly doing the same thing. It tends to use multi-magnification setting with a tendency toward the higher magnification. And the threshold here that I show is basically more than 8%. We repeated the same thing on the ovarian dataset, which is a more challenging dataset compared to the bladder or the TCGA1. And we saw really interesting result. Basically, the model for clear cell carcinoma, which is known for being diagnosed easier in lower magnification, is spending more energy on multi-magnification, but a tendency toward lower magnification. And so basically, these are the information that the pathologist gave me, that the clear cell carcinoma has characteristic low power architectures, but it needs to be excluded from high-grade serous carcinoma. So we need to make sure that is not high-grade serous carcinoma. So for high-grade serous carcinoma, we need to investigate different magnifications. So the model should make a wise decision here. The other subtype is endometrioid, which the model has tendency toward more low power compared to the clear cell carcinoma, but still it's distributed over different magnification. And low-grade serous carcinoma is very difficult in low power, and pathologists usually diagnose it in high power too. And that's the same thing that the model is doing, meaning that in 20x, it's spending around 36% of its 36% of the cases were diagnosed in 20x by the model. And lastly, for mucinous carcinoma and high-grade serous carcinoma, there is nothing that I can mention it. And for example, for the high-grade one, as you can see the green bars, it's kind of uniformly scattered. And high-grade serous carcinoma is the biggest group. It's around like 70% of ovarian carcinoma cases. And it's so diverse, even for the model, is the distribution or different magnification is basically uniform. And what is the pathologist saying is that, yes, it depending to the case, it needs to be diagnosed in different magnification. So there is no such a case that we always, when we want to diagnose, we say, let's go directly to the 20x. We need to investigate all the magnification to see what happens. And some of them are confirmed in lower magnification. Some of them are confirmed in higher magnification, or sometimes we need to go to higher, lower, higher, lower, lower, higher. This pattern repeatedly to confirm our diagnosis. And besides from the quantitative visualization, we have some qualitative visualization as well. So basically what we had was the so far we had the population-based study, and in this slide I'm going to go over the case-based study. In the case-based study, what we plotted is that is a histogram, is a heat map of the energy contribution and the features. So the first thing is that you may be curious about how's the energy contribution for different cases. For example, these are two random micropapillary cases from the data set. For one of them, the model has spent around 40% on 5x and 36% on 20x, which is shown in these bars. The first row is 5x and the third row is 20x. And as we can see, the middle row, which is 10x, is not as important for the model. Or for the other case, the model is picking only 10x for diagnosing. Around 67% of its energy has been allocated to 10x magnification. And this is basically showing that the model is picking the information case by case. It's not like that when the patches or the slides are similar, the model goes and picks just one magnification. Depending to the case and the feature, it still focuses on different magnification. And yes, it also shows the intra-magnification convergence. These are the features basically. And the last qualitative visualization is the patch level visualization. For the patch level visualization, what we did was basically, as we cannot fit all the patches from the slide into the memory because the patch size here is 1000 by 1000. So it's hard to fit all the patches from the slide and then go to the graph and backpropagate to visualize the heat maps of the model. So we just, let's say, pick these three patches that correspond to each other, 5x, 10x, and 20x, build a graph and pass it to the model, and then backpropagate to the vision encoder to have the patch level visualization. And what is showing is in lower magnification, as you can see, these are papillary. So we can basically understand that these are a pattern in the slide. The model is picking them as well. But this is the ROI for the higher power. When we go to the higher power, the model is still picking them. And then when it goes to the 20x, it's exactly targeting the micropapillary, not the cellular area that is not part of the tumor. So this is basically showing that the model, without any full supervision, could understand that it should targets different magnification and targets different patterns in different magnification and highlights them. And this is the same case for a urothelial case. That is, as you can see, it's harder to say what's the case here in lower magnification. So we need to go to higher magnification. And as you can see from the heat map, there is less activation here compared to the previous case. As we can see in the micropapillary, there is a lot of energy and activation here, more activation on 10x, less than 20x, more toward 5x and 10x. But for the urothelial case is different. For 5x and 10x, we don't see that much of activation, but as soon as it goes to 20x, the patterns are confirmed. So the model spends a lot of energy to highlight different patterns. So with these all, I want to thank you guys for your attention and would be happy to answer any questions.
That's brilliant. Thank you very much, Shay, for a really great talk. And so, yeah, with that, we'll open the floor to questions. Does anyone, either online or in person, have any questions to start with?
Yes. Can I ask a question?
Please, Mr. Go for it.
Oh, good. First of all, thank you, Ali, for the great presentation. I really enjoy reading your work and listening to it right now. So well done. Just a couple of quick questions. So the first one is more of a implementation-wise question. So I was wondering, like, what kind of batch size did you use to train this network? Because you have like nodes from all different magnifications in the network. So I wonder what kind of machine did you use to train the network, kind of batch size? What range of batch size did you use to train the network?
So that's a really good question. For the GPU, we had 3 different GPUs, RTX 6000, GPU 3090, and GPU A6000. But for the batch size, yes, because it's graph and its features, we can go higher batch size. The batch size here was 4.
4. Okay.
4 graphs, and the library was DGL, yes.
Okay. So my second question was, if you had looked into the, so I really like the way you've looked into the explainability and like sanity of what your model is doing in capturing interconnection of different magnifications, but was wondering that you've also looked into the node level explanation or contribution of nodes in terms of weight or scores or whatever toward the final prediction, to look for see that if for a certain prediction there are some patches in higher magnification heating up, the nodes that they are connected in the other magnification also showing up as well. Or no, it's just all the prediction are being done only based on one lower or higher magnification, sort of.
That's an excellent question. The thing is that it's not always the set of the nodes that matter. So as you, okay, if I go back here, the thing is that basically, okay, so let me go to this slide. So for example, for this case, the thing is that when you want to investigate the node level, 5x and 10x are not as important, because even for the humans, you cannot see that much here. So what stands out here is the 20x one, because that's the information we can confirm the subtype for. And in the node level information, if we want to get the nodes, because the level of gradient is different for each set of magnifications, then it's hard to confirm, it's hard to compare 2 magnifications together. What you can compare is basically the nodes within one magnification. You can compare them with 2 different magnification, but when the model converges, one of the magnification is way more important. So that node is like really important for the model, meaning that, okay, the lower magnification is not making me to make a decision. So let me just, I found a good one. Let me focus just on the good one. And that comes with the idea of the model that let's broadcast everything in the model together.
Okay, I see. Great, thank you. Adam, can I ask another question, please?
Yes, go for it, Mr. We've got some time.
Can you go back to the place that you were mathematically proving that the whole network can be summarized into 3 nodes? So I was wondering,
Yes.
so this is just me asking dumb question, but do you think if we change the way you form the graph, And change it, but in 3 levels, just what you said, but like connecting the nodes differently, right? Or extracting the patches differently. Would this theorem still hold?
No. So the theorem is because of the way that we form the GCN layers. So there is like we have a proof for the theorem. It's in the supplement, but it's still not on the public. I will make it public. But the thing is that the architecture of the graph and the way that these nodes summarizes are important. So currently there is this relationship that we can basically easily connect the information between the 2 levels of magnification. As soon as the magnification level graph gets a bit complicated and it's not a fully connected graph, it gets complicated. So it's get harder to make the theory. So for the fully connected graph, you have everything in the first neighborhood, they are connected. You can write the formula in the GCN and you can pass it. Because in the GCN, we have an activation. And in order to get rid of that activation, to get to an inequality, to get to this part, you need that. If you don't have it, you either need to drop the activation from your model. If you don't need any nonlinear activation, if you want to make the graph more complicated, or if you use that complicated, you need to make the graph more simple. So that's the bottleneck here from theoretical point of view.
I see. And final question, is this code publicly available, your implementation of the model?
Our model is still under review, but we will publish the code and everything.
All right. Anyway, thank you very much. Well done.
Thank you.
Yeah, thanks, Mr. Blair. So we've also got a question online from Jack Breen, who said, that was great, thanks. Could you explain the magnifications and patches used in model comparisons? For example, in attention-based MIL, did your patches cover the entire whole slide image at 20x, or did it cover a similar portion of the whole slide image that covered in the graph model?
So yes, because we wanted to make a fair comparison, we fed the same set of patches to the ABMIL. But the thing is that the standard for ABMIL is 20x, what they did in their paper. So we reported only 20x in the paper. We have done experiment on 5x and 10x with the same patches for the model. And also I've done experiment that I basically give all the patches, all the encodings from all 3 magnification to ABMIL. And it was interesting because the performance sometimes drops when you give all the patches from 3 different magnification together to a ABMIL model, because that model doesn't understand magnification. So, but for the publication part, we just put the 20x, which is a standard out. But the thing is that we wanted to make sure that the architecture has an improvement. We did like different experiments and we saw for 5x, 10x, and 20x separately and a combination of them all. And the thing is that they usually do better on 20x. And this is their, I think, original architecture is 20x too.
Okay. Thank you, Ali. So do we have any more questions from anyone in person or anyone online as well?
I guess another quick question about the convergence.
Can you hear that? Sorry, Ali.
Can you repeat it?
Basically, just another question about the convergence. I'm not clear what is the rationale behind trying to make that convergence happen? Because, for example, if we want to do any sort of node prediction, if all of the nodes are converging to the same kind of representation, doesn't that limit in certain ways the things you can do with this sort of graph? Is there not a way you can keep the hierarchical structure while also maintaining like a difference in the representation of nodes? Does that make sense?
So I think your question is for this part, so you would say why the convergence matters, right?
Yeah.
Okay, so the thing is that we have this convergence in other model as well, but the thing is that we call it pooling. So the way that they basically do a lot of operation and at the end they pool. So
I
maybe
guess
max
in the
pooling
case of pooling, you kind of choose to do it at a certain point, and you have the unpooled results there if you need to with them. Whereas if it's kind of baked into the architecture and it happens outside of a pooling, outside of a specific pooling step, you don't have that information there anymore, even if you want to do something with it.
Yes, the thing is that here the idea is basically the idea of broadcasting and reaching to all the nodes is that, so if there is any important information in any node, it should reaches out to all the nodes. So, and that's the thing. So if the important information is here, it will passes to all the nodes. And if the model is doing good, it will get that information. If your features are good, it's gonna pass to all the nodes, and yeah, that's there. So, and when it's the convergence happens, it's basically magnification level, and with that broadcasting, we don't need to choose to pool anymore because the information is there. So the model itself converges to that node. Because
I guess
the thing is that
whole question I'm asking is, if you had a node level target, is there a way about adapting this architecture such that you do that sort of prediction task, or is it purely designed for graph level prediction?
okay, so this was designed for graph classification. So I didn't do it on node classification, but I think the difference is on the convolutional layer. If we change the convolution, basically this property may not be hold. So if we change it from GCN to something else, a bit more complicated, this is not going to converge anymore. So we may need to change it. And for node level classification, we use a different set of training, and basically everything changes a bit. So I doubt it that it converges.
Okay. Thank you. Great. Thanks, Ali. Thanks, Mark. So does anyone else have any questions, either in person or online? If not, then I'll finish with a final question then. So what do you think, what would you say then from your experience of this work are the next steps to the field of computational pathology? Let's say, particularly in terms of relating this sort of model to, say, foundation models, or
So yes, the thing that we realized with this work is basically your encoder matters. So, and the thing is that all the encoders that we have are only trained on 20x. Even foundation models are only 20x. So basically our foundation models are blind for lower magnification. So that's the thing here. If we want to have a really good foundation model, the first thing is to have the model need to understand different magnification. Yes, people use scaling and augmentation in their training, but that doesn't do it. We need to have an architecturally informed model that can understand different magnification to get pooling. And I've not shown it here, but we have done experiments that we extracted features from lower magnification and compared it with higher magnification. And the thing is that when you do with a foundation model or like frequency transpass models that we have, the quality of the embedding is not as good in lower magnification compared to the higher magnification. So that's still like a problem in the field that we need to work on it and improve it and get a better result.
Thank you. Although we have had a couple more questions just coming in the last few minutes. So Mustafa said, on foundation model, the new uni model has shown to be magnification agnostic, a little bit anyway. And Jack says the uni foundation model seems to apply really well to lower magnifications, despite the training being at 28 in his specific experience. But yeah, so no questions, just comments. But no, thank you very much, Ali. That's a really interesting talk. And I think with this, we'll draw the seminar to a close. But yeah, best of luck with your future work. And thank you to everyone that's attended both online and in person. And a reminder that our next seminar is in 2 weeks' time on Monday, the 13th of May. Next week's bank holiday. And it's at the same time from 2 till 3 p.m, where we're delighted to be joined online by Dr. Sebastian Pine from Essen in Germany. But again, thank you very much, Ali, for a really interesting talk. And yeah, best of luck with your future work.
Thank you for having me. And yeah, it was a pleasure to present our work here. Thank you.
Thanks, Ali.
Thank you, Ali. Thanks, Adam. Bye, everyone.
Bye, everyone.